Okay, so let's do an example of iterated integration. So the problem on your screen is use an iterated integral to find the area of the region bounded by the graphs of the equations. And we're given y equals x to the 3 over 2 and y equals 4x. So first we need to graph the equations so that we have an idea what the area between their graphs might look like. So y equals 4x, I know is going to be a line with positive slope, something like that. And y equals x to the 3 over 2 is going to look something like that. So here, this is y equal to 4x. This is y equal to x to the 3 halves. And I'm going to need to know a little bit about this point of intersection. So I'm going to set the two functions equal to each other and solve for the x value. So 4x equals x to the 3 over 2. So 4x minus x to the 3 over 2 equals 0. And if I factor out an x, I get 4 minus square root of x is equal to 0. So I find x equals 0, which is this point at the origin. I also find 4 minus square root of x equals 0. So that would be 4 equals square root of x, or 16 equals x. So that tells me my x value out here is 16. And then I can just plug back into either of the functions. So 16 times 4 is 64. So I know that the 2 points of intersection are 0, 0, the origin, and 16, 64. Now I want to find the area. So I'll think about a small rectangle sitting here. And it looks like, if I'm thinking about the change in y, I am going from the bottom curve, which is x to the 3 over 2, to the top curve 4x. That's dy, the change in y. And then I need to multiply by the change in x. And I think about x is varying from where to where, and it looks like if I took an intermediate point anywhere, I would be between 0 and 16. If I drop this perpendicular, I see that the point where it reaches the x-axis is 16, 0. So I'm going to say between 0 and 16. And now I do the calculation. So I'm starting from the inside out, so I'm going to keep 0 to 16 here. And the first integration inside is going to be integration of dy is y. I want to evaluate from x to the 3 halves to 4x. And then I'm going to integrate that with respect to x. So that's going to be integration from 0 to 16. And inside I get 4x minus x to the 3 over 2, just by evaluating y at the two limits, dx. And now this looks like a simple integration in x. So I can say when I take the antiderivative of 4x, I get 4x squared over 2, so that's just 2x squared. When I take the antiderivative of minus x to the 3 over 2, I want to add 1 to the power, so the power of x is going to become 5 over 2. Then I need to divide by 5 over 2, which is multiplying by 2/5. So I have 2x squared minus 2/5 x to the 5 over 2, and I need to evaluate at 0 and 16. So first, 16, that's 2 times 16 squared minus 2/5 times 16 to the 5/2. And then I would subtract these functions evaluated at 0. And it looks like if I plug in 0 to either one, I get 0. So that's just going to be minus 0. Or minus 0 plus 0 if you want. And so let's just simplify here. I know that 16 squared is 256. So I have 2 times 256 minus 2/5. And what I've got inside the parentheses here, I can think of as 16 to the 1/2 to the 5th. Or in other words, 16 to the 1/2 is 4. So 4 to the 5th. And I would like to think of 4 to the power 5 as 4 squared, which is 16, times 4 squared, which is 16 times 4. So 16 squared times 4, because I know that 16 squared is 256. So I've got 2 times 256 minus 2/5 times 4 times 256. I want to find a common denominator, and I'm going to say this is 10/5 times 256 minus 8/5 times 256, which is 2/5 times 256, which is 5/12/5. So 5/12/5 should be the area between these two curves above the x-axis.